Hello everyone, this is a challenge question walkthrough for Edexcel's Pure Year 2 textbook, Chapter 11. Okay, our first question is from exercise 11b, and we're given this integral from 5 to 11 of 1 over ax plus b dx is equal to 1 over a ln 41 over 17, and a and b are integers with 0 is less than a is less than 10, and we're asked to find two different pairs of values for a and b. So let's just start off by working out what this integral is. So the integral from 5 to 11 of 1 over ax plus b dx. Now here, because we have a fraction with a linear term in the denominator and just 1 on the top, then this is equal to ln of ax plus b, but the reverse chain rule says we have to do divide by the derivative of the inside here, so that means we have to divide by a, so we put 1 over a out in front there, and that's from 5 to 11. And evaluating this, we start by putting 11 in, so 1 over a ln 11a plus b, and then we're taking away 1 over a ln 5a plus b. Okay. And now we can use laws of logarithms here. So if we first factorise that 1 over a out, we get 1 over a times 11 ln 11a plus b, take away ln of 5a plus b. And the laws of logarithms means we can rewrite this inside the bracket here as ln of 11a plus b over 5a plus b, and we're told that that equals 1 over a ln of 41 over 17. So from that we get that 11a plus b is equal to 41 and 5a plus b is equal to 17. Now, taking away these two equations, we're left with 6a, the b's cancel, is equal to 41, take away 17, which is 24. So a is equal to 4. And 4 is between 0 and 10, so we're okay. Then, putting this back into the top equation here, gives us 44 plus b equals 41. So b is equal to minus 3. So now we've got a equals 4 and b equals minus 3 as one possible pair of values for a and b. But notice that the question asks us for two different pairs of values, which is a bit confusing, right? But because we've got that this fraction here equals 41 over 17, means that actually we could have that 11a plus b equals 82, and 5a plus b is equal to 34. And 82 over 34 will still give you 41 over 17. So maybe this will give us another pair of values for a and b. So let's have a look. Taking away the two equations again, this time using 82 and 34, we get 6a is equal to 82 take away 34, which is 48, which means our a now is 8. And putting that back into the top equation, 11 times a is 88, plus b equals 82, so b equals minus 6. So our two pairs of values for a and b are either 4 and minus 3, or 8 and minus 6. Okay, and our next question is from exercise 11e. By using a substitution of the form x equals k sine u, show that the integral of 1 over x squared times the square root of 9 minus x squared dx is equal to minus the square root of 9 minus x squared over 9x plus c. So we're given a big clue here that the substitution we want to use is of the form x equals some number times sine u. And looking at this integral here, we've got the big problem, which is the square root of 9 minus x squared, right? So we want to pick a value of k so that when we have when we substitute x equals k sine u into this, we get 9 minus k squared sine squared u. So substituting that value of x that we chose into the expression here, then we want this to simplify nicely. And to do this, we can use the identity 1 minus sine squared theta equals cos squared theta. But to do this, we ideally want this k squared here to be equal to 9, so that we can factor out 9. And we can do that by letting k equal 3, right? So if we let our substitution be x equals 3 sine u, then that means differentiating both sides by u, we're going to have dx by du on the left hand side, and the right hand side differentiates to 3 cos u. So we have dx is equal to 3 cos u du. Okay, so if we put all of this together into this integral here and substitute it all in, then we're going to have this integral is equal to the integral of 1 over, now x squared is 3 sine u squared, so 9 sine squared u. Then we have the square root of 9 minus 9 sine squared u. And then we have dx being replaced by 3 cos u du. Okay, so let's focus in on this this square root here. If we take out a factor of 9 first, then we're left with 1 minus sine squared u, which we know is equal to cos squared u. So we have 9 cos squared u square rooted, which is just 3 cos u. So actually this whole square root and 3 cos u cancel. So we're left with the integral of 1 over 9 sine squared u du. And we know that 1 over sine squared u is equal to cosec squared u. So this is equal to, if we can, if we take out the 1/9, but then we have this is equal to 1/9 of the integral of cosec squared u du, which you know is minus cot u. So we have minus cot u over 9 plus c. And now we need to get this back into the world of x. So cot u we know is equal to cos u over sin u. And from here, this original substitution equation up here, we can rearrange to find what sin u is. So sin u is equal to x over 3. And for cos of u, we need to use the identity up here again to find that cos of u is equal to the square root of 1 minus sine squared u. And we know what sin u is, it's x over 3. So this is equal to 1 minus x over 3 squared. Okay, so now we have all the information we need to rewrite minus cot u over 9 plus c in terms of x. And we're aiming for this up here. So let's have a go. So cot u we know is equal to cos u over sine of u. So we have minus cos u over 9 sine u plus c. And cos u we know is equal to the square root of 1 take away 1 minus x over 3 squared, so x squared over 9. And that's all over 9 sine u, which is 9 times x over 3. So we have minus square root of 1 minus x squared over 9 over 9. 9 times x over 3 is 3x. Now if we compare this to the answer that we're looking for, on the numerator we have the square root of 9 minus x squared. So if we take out a factor of 1/9 from the top, so we're multiplying everything inside by 9 because we're dividing by 9 outside now. So that gives us a 9th of 9 minus x squared, which is what we're looking for, all over 3x. So to take the 9th outside of the square root, we need to square root it. So the square root of the 9th comes outside, which is just a third. And then to get rid of the third on the numerator, sorry I forgot the minus there, we need to multiply top and bottom by 3. So we're left with 9 minus x squared, all square rooted, over 9x. Add on the plus c as required. Okay, the next question comes from exercise 11H, and we're given a diagram with the two curves y equals sine 2x and y equals cos x between 0 and pi over 4. We're asked to find the exact value of the total shaded area on the diagram. So, if we first think about what areas we need to find here, well, we can see the shaded area split into two distinct bits, right? So we have the area to the left of this dotted line and to the right. And if we first focus on finding this area and then look at that area, we first need to find where these two curves intersect, right? So that will be where y equals sine 2x and y equals cos x are equal. So sine 2x equals cos x. And I think the easiest way to solve this would be to use the double angle formula for sine. So sine 2x we know is 2 sine x cos x. Okay. And because we are between 0 and pi over 4, we can divide by cos of x safely, knowing that it can't be equal to 0. So we have 2 sine x is equal to 1. So sine of x is equal to a half, which means that x is going to be pi over 6 in radians. Okay, so this bit there is pi over 6. So for the first area, we're going to be integrating between 0 and pi over 6. Now the top curve, the red curve, is y equals cos of x. So that goes first. And then we're taking away the area underneath the black curve, which is sine of 2x dx. Okay, so this will give us cos of x being integrated to sine of x, and minus sine 2x becomes, being really careful with this one, positive 1/2 cos 2x. Using the reverse chain rule and remembering that sine goes to negative cos, but because we've got a minus here already, we get positive half cos 2x between 0 and pi over 6. So evaluating these limits, pi over 6 goes first, substituting that in for x. So 2 of x will be pi over 3. Then taking away the same thing with x being equal to 0. Now sine pi over 6 we know is a half, plus a half cos of pi over 3, which is also a half. Then we're taking away sine 0, which is 0, and a half of cos 0 is just a half. So we get a half plus a quarter, minus 0 minus a half. These halves cancel, the 0 doesn't make any difference, so we're left with a quarter. So the area of 1 is a quarter. And doing a similar sort of thing for the second area, doing the integral this time from pi over 6 to pi over 4. And this time the black curve is on top, so we're doing sine of 2x first, taking away the cos of x underneath. So similar sort of thing, this time the sine 2 of x is going to integrate to minus a half cos 2x. And the minus cos of x is going to integrate to minus sine x. Between pi over 6 and pi over 4. Okay, and that gives us a half cos of pi over 2 minus sine of pi over 4. And then we're going to take away, substituting pi over 6 in, minus a half cos of pi over 3 minus sine of pi over 6. And quickly simplifying, we know that cos of pi over 2 is 0, so this sum cancels. And we've got minus sine of pi over 4, so minus root 2 over 2. And they're taking away minus a half cos pi over 3, so that's plus a quarter. And then we're taking away minus sine of pi over 6, so we're going to add a half. So this area is equal to 3/4 take away root 2 over 2. Add that on to the quarter down there. So the total area is equal to 3/4 minus root 2 over 2 plus a quarter, which is equal to 1 minus root 2 over 2. Okay, and our last question is from mixed exercise 11. Given f of x equals x squared minus x minus 2, we're asked to find these two integrals. Starting with this first one from part A, the integral from minus 3 to 3 of the modulus of f of x dx. Now when working with modulus functions, it's always a good idea to draw a graph so we know what's happening. So x squared minus x minus 2 factorizes to give x minus 2, x plus 1. So we know it has two roots at x equals 2 and x equals minus 1. So let's put that here and here. And we know it goes through the y-axis at minus 2. So it goes something like that. And because it's a modulus graph, everything that's underneath the x-axis, gets reflected upwards. So our graph ends up looking something like this. Okay, and we were asked to find the integral between minus 3 and 3. So this point here is minus 1, this point here is 2. So we're trying to find the integral between minus 3, which is somewhere here, and positive 3, which is somewhere here. So we're trying to find the area here. Okay. So we're going to have to split this into 3 sections, thinking carefully about how each section is going to work. So let's call them 1, 2, and 3. For this first section here, we're going to have the integral from minus 3 to minus 1 of positive f of x. So this is where f of x is above the x-axis naturally, before we even take the modulus sign. So the integral from minus 3 to minus 1 of just f of x, x squared minus x minus 2. Okay, and then for the second area, now this is slightly different because originally the integral between minus 1 and 2 would be negative, right? But now it's a positive area because it's above the x-axis. So we actually need to take the integral. Well, actually, we can do this in 2 ways. We can either add on the integral from minus 1 to 2 of negative f of x. So that's minus x squared plus x plus 2 dx. Or we could have just taken away the integral from minus 1 to 2 of x squared minus x minus 2. Either way works just fine because we're essentially doing the same thing, just introducing a negative somewhere there, whether it's outside here or inside the bracket. But let's go with that. And then finally, the last part is the third area, which is from 2 to 3 of the curve where it's positive. So we're keeping the same x squared minus x minus 2 dx. Okay, so this shouldn't be too much of a pain to integrate now. We have a third x cubed minus a half x squared minus 2x from minus 3 to minus 1. And then we've got here minus a third x cubed plus a half x squared plus 2x from minus 1 to 2. And then we're adding on here a third x cubed minus a half x squared minus 2x from 2 to 3. I won't bore you with writing out all of this, so I'm just going to tell you the answer at the end should be 15 once you've calculated all of these limits. And just to quickly note, another method which is perhaps more efficient would have been to take the integral of minus 3 to 3 of f of x, and just note that that would have given you this area 1 here, then a negative lot of area 2, and then area 3. So to get the area 1 plus 2 plus 3, we would add on 2 lots of the area 2. So we would take the integral from minus 3 to 3 of f of x dx, and then add on 2 lots of the integral from minus 1 to 2 of minus f of x dx. And that's another way to go about this problem. Okay, and for part B, we're going to be doing something quite similar, but instead of having the modulus of f of x, we've now got f of the modulus of x. So very slightly different, but the curve will actually look very different. So instead of flipping everything underneath the x-axis above it, we're just going to have the curve reflected so everything that's to the right of the y-axis, so all of this of the curve is just going to be reflected in the y-axis, so like that. So this is our graph of y equals f of the modulus of x, and we know that it meets the y-axis at -2. We need to find the integral from 3 to -3. So again, something that looks like this, where this is -3 and this is 3. We're looking for the integral between here. So the area is this positive area here, this positive area here, and then taking away all this negative area here. So to do this, we can just find this purple area here on the right hand side and then just double it, because then we have another lot of that area there and another lot of that area there. So all we need to do is find the value of the integral between 0 and 3 and then just double it. So what we're looking for, the integral between -3 and 3 of f of the modulus of x is actually just equal to 2 lots of the integral from 0 to 3 of f of x. And this is equal to 2 lots of, well, the integral of f of x is a third x cubed minus a half x squared minus 2x, as we've said before. Now, when we substitute 0 in there, we get 0. So all we're interested in is the first bracket, where we substitute 3 in. So a third times 3 cubed, which is 27, minus a half times 3 squared, which is 9, minus 2 times 3, which is 6. So we have 2 lots of 9 minus 9 halves minus 6, which is 2 times minus 3 halves, which is just -3. And that is our answer. And that is the end of the challenge question walkthrough for Edexcel's Pure Year 2 Chapter 11. I hope you enjoyed, and I'll see you next time.